Ever wonder how an app actually survives going viral? It's not just about throwing more servers at the problem. Nope, it's about a much smarter architecture. Today, we are pulling back the curtain on one of the biggest secrets to massive scale, the message queue.
Alright, so picture this. You've just spent months, maybe even years, building this amazing AI photo generator. You've polished every pixel, tuned the model, and finally, you hit that big, beautiful launch button. Your app is officially out in the wild. And then it happens. The dream. Some huge influencer posts about it. You hit the front page of Reddit. The download numbers are just going absolutely vertical. This is it. This is what you've been working for. But then the dream starts to curdle. Just as fast as the users pour in, your phone starts blowing up with server alerts. Your beautiful creation is literally buckling under its own success.
So here's the fatal flaw, the ticking time bomb in your architecture. Each AI photo generation is a heavy lift, right? It takes a full 10 seconds. And in your current setup, when a user clicks generate, they're completely locked in. Think of it like a rigid, red-hot line connecting them directly to one of your servers, which is now sweating, totally tied up for 10 long seconds, and completely unable to help anyone else.
So what happens when thousands of people hit generate at the same time? Well, your servers don't just slow down, they completely melt, and every single new user is greeted with that dreaded error, 504 gateway timeout. Your viral launch has just turned into a viral failure.
Okay, so how do we fix this disaster? We can't really make the AI faster, at least not overnight. But what we can do is totally change how we handle the work. And this, my friends, is where the architectural magic happens. We introduce a message queue. I want you to think of this thing as like a glowing neon green buffer zone that sits right between the user's request and all that heavy lifting. It's a special component, and its entire job is just to catch tasks and hold on to them safely. This enables something called asynchronous communication.
So check out the new flow. It's beautiful. A user requests an image. The web server, we'll call it the producer, it doesn't do the hard work itself. No way. It just drops a cute little message, a data packet, into the queue and instantly tells the user, hey, we got it. We're on it. The user isn't stuck waiting. The web server is immediately free for the next person, and the job is tucked away, safe and sound, in the queue.
This one simple change unlocks an architectural superpower, and you're going to hear this word a lot, decoupling. This is absolutely crucial. It means our web servers and our photo processing servers, they don't even have to know about each other anymore. They operate completely independently.
Okay, so here's the play-by-play. It's actually super simple. 1. Our web servers, the producers, just fire and forget. They publish tasks to the queue. 2. The queue just holds them. That's its job. 3. A totally separate group of servers are consumers or workers. They pull tasks from the queue whenever they have a free moment, at their own pace. And 4. And this is the real game changer. If that queue starts getting long, we just spin up more consumer servers. The web servers, they don't even notice. They're totally protected from the chaos.
I mean, just look at the difference here. The old way, that was synchronous, tightly coupled, and just brittle. Super fragile. One slow part could crash the whole thing. But the new way, it's asynchronous, it's decoupled, it's non-blocking, and it is incredibly resilient. Your system can now handle these massive, spiky workloads without even breaking a sweat.
And look, this isn't some abstract, theoretical trick. This is how pretty much every major tech company on the planet operates at scale. Let's look at a perfect example you probably use every day.
Ever wonder about this? You're booking an Uber, right? Your phone goes into a tunnel, loses service for a few seconds, but your request still goes through. How does that even work?
It's because they use a powerful message broker, something like Kafka. When you hit Request Ride, your app doesn't talk directly to a driver. No, it sends a message to Uber's system, and that message is immediately tucked away safely in a queue. So even if your driver's phone, the recipient, is temporarily offline in that tunnel, the queue just holds on to that request. As soon as their phone gets a signal again, boom, it pulls the message and gets the ride. No data is lost. The sender and the receiver don't even need to be online at the same time. Now that is resilience.
All right, so we did it. By putting in a message queue, we've totally solved our viral overload problem. But here's a secret of system design. Solving one bottleneck, well, it always reveals the next one.
But first, let's just take a moment and celebrate. Our system for handling these big, slow background jobs is now robust, it's scalable, it's practically invincible. We can handle millions of photo generations. We are absolutely crushing it.
But hang on. All those users, all those photos, all that metadata, it's got to be stored somewhere, right? Our main database is now growing by terabytes a day. You can almost see it starting to crack under the pressure. And this time, just adding more RAM isn't going to save us.
So what do you do when your database becomes one giant single point of failure? Well, you slice it into pieces. Tomorrow we're going to dive into database sharding, the technique for scaling your data basically to infinity. I'll see you then.